Hello, everyone.
Hello, everyone. Thank you so much for coming and for attending this workshop. We did not expect such a turnout. It's actually way more than we expected. So welcome. My name is Bardia, and I'll be telling you about generative AI today. This workshop was organized and brought to you by three associations, three institutions, whatever you want to call it. Student Association of Cognitive Science, SACS, represented by Yarance. Encode Justice Canada, represented by Cleo and Tweed. And the Mcgill AI Society, Society, which I think is represented by Miriam, she's here. But anyways, all to say that these guys did a lot of work to organize this, and we thank them very much. My name is Bardia. As I told you once, I'm a U3 Coxside Mcgill student, and I've been playing around with GPT-2 since 2019, like LLMs from that era when Transformers first came out and they got trained on some data and they started generating cool texts. And then text-to-image models came by around 2021 with BQGAN plus Clip. We're going to talk more about that. And I was playing around with that too, and I was so interested that I ended up contributing some code to an animation tool, open source animation tool kit on GitHub called The Forum. I do research in AI, cognitive environments and processes, game development, and content creation. If you want to see some cool papers, you can follow me on Twitter. If you want to see some cool stuff I've made with these generative AI technologies, you can check out my Instagram or TikTok. And if you want to see some of the more like mathy researchy things that I've maybe worked on, like posted on GitHub, you can follow me GitHub there. Who are you? You guys are mostly composed of cognitive science and computer science, not engineers, students. And then we have neuroscience, or applied AI, software engineering, and then we have a whole array of different types of disciplines, which shows that this interest in this workshop is not singular, and that there's potential for it to be used in many, many applications and domains. So here's a table of contents. We're first going to talk about generative AI, AIs, and neural nets, go over the neural nets for a little bit, see how they work, and then I'm going to talk about two specific generative architectures, which are the transformers and diffusion models, and how they work. Then we're going to follow it up with some AI ethics, and there's a glossary at the end if you forget what something is, like overall. My goal here is not to tell you, this is what you need to do, and these are the algorithms you need to write or everything or stuff like that. I'm here to basically fast track you and give you like a guide so that you're able to start and get yourself to a place where you can start creating and building stuff. I'll continue. So what is generative AI? And generative AI is any sort of AI model that outputs data that humans can recognize, that humans can use, that we understand, that is not a classification, but rather just raw data that we know. But then we say AI, and what is AI? And we talk about AI all the time, and there's all sorts of stuff going on in the media, AI this, AI that, ChatGPT is going to kill us. But really, AI is just a computer program that mimics human intelligence. And there's two kinds. There's rule-based, which is if then rules, if this happens, then do that. If you see, it's like in video games, if you see an enemy, shoot him. It's very, very simple, rule-based. And then we have statistical AI, which is the topic of today's talk, and most of the AI that we refer to nowadays is all statistical AI. So basically, we've taken statistics and we've reframed it as machine learning, and then we've reframed it as artificial intelligence, and we're good at selling it to rich old men who do not know what they're talking about. So neural networks, what are they? Very simple. 3 parts. They have 3 parts. They compose of weights, a loss function, and an optimizer. And it's very simple what these three things represent. So first, I'd like to ask someone or anyone in the room who is willing to find the difference between these two pictures. There's the picture. Basically, any graph that we call a neural network and that we built is a series of multiplications that you've probably seen in high school. This part, right? It's just the sum of some terms. That's it. And we basically take this to a higher level. We do it on lists of numbers, and we do matrix multiplications. And the way we explain to the computer that I want to do this matrix multiplication is like this thing up there. You know, for the people on Zoom, this is what you write in your program. This is what you read in high school. This is what you learned college, early university is linear algebra. Very simple. What you basically do is you take the two weights here, and then you like collapse them. You multiply like that. So W0 goes to X0, W2 goes to X1, and then you sum it all up, and then you get the Y0. You do that for everything, and then you add the biases, like add two numbers at the end. This is a very, very basic representation of a neural network, but it's not fully a neural network yet, and you'll see why. But we can see the weights, which is basically, as we saw here, for every Y that we have there, we are summing up all the arrows that's going into it. Same thing here. Then we add the biases, just another list of numbers, not a big deal, super straightforward. And then we add this function, which is like, we call it a nonlinear function. What it does is basically it allows you to have edges and corners in the space that you're navigating. And the space is defined by the number of parameters. Now, in real world, we have 3D space, you know, X, Y, and Z, but here we can have more. And what you really need to care about is just a bunch of numbers, like not a big deal, just multiplication. So what we're trying to do at the end is that we're trying to give it some input, X, and then we're trying to get some output Y. In most cases, we have X and we have Y, and what we're trying to find is W and B, which is the weights and the biases. So in order to find that, we need a loss function. Loss function looks at that neural network and its output, and it looks and says, is this output what I want? Basically, here's an example. The MSE, mean squared error. You have the output of the model, which is yi, and then you have the expected output, which is y hat I, and then you find the distance between them, and then you take the average for all of it. Super simple. And then we need to optimize. Well, basically, this gives us a way to compare the outputs with what we expect. And we optimize it by finding the path to the lowest loss. And the loss, we define it in that space. So there's a space of if you have two parameters, the loss is the depth, and the two parameters is like the flat surface and like the XY coordinates. Sorry, the X and Z coordinates actually. And then you're trying to find the lowest point in that space. Now you can have that same thing in a higher dimension. This is an example of it in a higher dimension. So here, Dory and Marlin are like parameters. The light over there over time is like the global minimum of darkness, and then finding the path to the light is basically the task of optimization. And one of the most simple examples is a gradient descent algorithm, which basically takes the weights and goes in the opposite direction of the loss. So whatever each weight contributed to the mistake, now go the opposite direction a little bit. So the whole thing gets summed up in these three parts. And you can basically write it as a very simple, small program here that you can run it in Google Colab if you want. Super, and you super simple. You'll see that the x's here are random. We've given random y's. And then always you start with random weights and biases, but these are usually in actual application, actual values that you're looking for. And you'll see that when we run this code, it actually landed really fast. The first step, this was the difference between what the output gave and what we expected it, and this difference diminished. It went down. So that's optimization for you. Every neural network works basically on these principles. So next, generative architectures. So we've built up some of these neural networks. We've created these massive neural nets with different functions, different sort of types of like activation functions, and then you add some stuff in between, latent spaces. You add other architectures, you add other like neural networks of different types, and you basically work them together, and you get really useful stuff. And two of the most recent generative architectures that have come out and that are super good are these two: the transformer and the diffusion model. Now, diffusion is a method of training, not exactly a model, but we're putting them in the same class. So they're both composed of encoders and decoders. Encoders basically take some data and gives you a compact representation of what it's supposed to be. A decoder takes that compact representation and then unpacks it to give you the data. So what's really happening in a transformer or in a diffusion model, it's both the same thing. You compress some data, and then you get something out of it. Now, what is that data that you compress? That depends on the architecture. So first, we're going to talk about transformers. Transformers, this is the basic inside of the structure. You don't really need to know this. I just put it here just for the sake of completion. But there's one thing that's really talked about. It's the masked multi-head attention, which is just an attention mechanism. Is when you take you find that if you have, let's say, some text and you want to see how it relates to itself, you create basically a matrix, which is also a graph, as we saw, that shows the dependencies of these words relative to each other, and then it can use that in the network to produce to see what word is supposed to come next. So transformers were first built for translation as a replacement for a technique called sequence to sequence, sec to sec. And it basically takes as an encoder a sentence in English, and it takes for the decoder the same thing but in French, and then it learns to basically, next time we won't give it this part, and we just give it a sentence in English through the encoder, and then it gives us the French version. Language models, like GPT-2, they take off this encoder part, and then take the words and we tokenize it. What does tokenization means? It's literally this. You break it up into parts that are most likely to appear in text. And the reason it's most likely to appear is because you want to reduce the dimensions of how many basically unique kinds of tokens you have, so that your model is smaller. So you can do the same thing with vision. You take some images, you encode them, basically compress the representation into a bunch of numbers, pass it into the encoder, you pass a description, the model learns to output the description. All of them are tokenized, meaning that they get a specific index or value attached to like different parts of it. And how you do these encodings are different from like case by case. And then we have, Donut, for example, is another vision model. The way it works is instead of it going to the encoder, it takes that image and it just adds, puts it before the description. It's like ChatGPT. You go in, you put in a bunch of numbers, and then you put in some text, and then eventually you teach it to learn how to represent that as that, represent the images as descriptions. You can do the same thing with speech to text. Speech to text takes raw audio signal, divides it up, learns its features, which is shown here as the representations, like the different kinds of patterns of speech that might appear, and then associates it. So in short, transformers are an association machine. They're really good at associating stuff together. We just need to turn them into tokens before we do anything. And the way to do that is just use an encoder. And we have different kinds for different purposes. You can also give it financial data and make money off of it if you have the capital. I don't. So we have, here's some examples. I posted them here. One of the more interesting ones is this latest one by Meta. I have it here. Basically, it allows you to do speech to speech, speech to text. It takes your expression when you're trying to speak and tries to incorporate that. I put a link here. I'm not going to try it right now. It might be low on time. If we're not, I might check. So basically, some examples, and you can find plenty of stuff on Hugging Face. And Hugging Face is where all the open source models go nowadays. If you make a model and you want it to be seen by people, You go on Hugging Face, you upload it there, and everybody can use it. They can give you feedback on it, and so on. Here's some vision transformers. Basically takes an image, takes a description, tries to associate them. Clip is one we're going to be talking about a lot. It was developed by OpenAI in 2021. Donut is for documents and receipt processing. Nougat came out after Donut. It was a fine-tune of Donut by Meta, and it basically does PDF to text. I don't know if you ever had this before. ChatGPT had vision. You couldn't like if you wanted to like put some PDF into it, you couldn't do that. And basically you had math equations or like tables and stuff. Well, Nougat takes care of all of that. Basically turns it all to plain text format. And then GPT-4, which was also trained on vision, which is probably the same thing as Donut. I don't think there's a specific encoder for it. It might all be decoded, but I'm just guessing. Then we have the large language models that you all have heard of. We started with GPT-2 in 2019. There have been some way before, but we're going to talk about that. We had BERT by Microsoft. Phi 2 is recent. It's a small language model. It was actually, turns out this was trained on test data, so I don't know how reliable it is. Then we have GPT-4, GPT 3.5, Llama, and Mixtral is great. I'll show you an interface where to use it too. So, transformers. They were originally made for translation. What they do is they predict the next token given the previous tokens, and then feeds itself back, feeds the output back to itself. So we call that autoregressive. It's a weird name, but that's what it means. It's like recursive. Size matters. The bigger your transformer, usually the better, but not always. You still have to have a good model. You have to have good data. You have to teach it, you know, in sort of a systemic way. You need to have a good tokenizer. There's a lot that goes into it. It's not just size, but size matters a lot. That's why people are trying to push for larger and larger models. And another thing is that they have purely semantic understanding. So you can't expect, you know, a language model, which is just language, to tell you to find basically rhymes in like if you want to do like rhyming or like poems. You can't do that because it doesn't have that data naturally. You can augment the data, but that's a different story. Maybe we'll talk about that in the next workshop. And they're multi-modal association machines. Just what you need to know is that they associate stuff with each other. They associate data. So large language models, some practical stuff here. Before that, a little bit of history. They started with engrams, 1950s, I think. And then we had hidden Markov models, 1966. All of these, you can find the papers here if you're more interested to read about them. Then we had RNNs, and we have LSTMs. And we have neural network language models, 2003 by Benji. If you know, I'm sure a lot of you know. Word2Vec. This is not a language model, but it's used for language processing, and it's very useful. We'll talk about this later in the next workshop, if a chance comes. And then we had Glove, which was like a variant of Word2Vec. And then we had sequence to sequence, and then we had transformers, which was just like blew everyone out of the water, and we were just like, that's the thing, and that's the shit. Excuse my language. So alignment. So we see in a lot of models today, like GPTs and almost every model you can use commercially, they are aligned in two ways. One is they're instruction aligned, and the other one is they're safety aligned. Alignment is done using reinforcement learning. Reinforcement learning means you look at the model and you basically punish it every time it doesn't give you what you want, and you reward it every time it does what you want. And all language models come out at the very beginning unaligned. So they do not have this alignment. They do not follow instructions. Instead, what they do is that they're autocompletes. They complete your text. They guess what's coming next. And then when you instruct align it, you give it commands. So I have two examples here. Is like if you want to prompt an unaligned model, you say, here's a list of 10 egg-based recipes. You've created the expectation that it's going to give you an answer. Or you say, let's correct this, and then you give it the text. And then when after instruction alignment, you just give it a command. Hey, write me this, correct this, do that. And then we have safety alignment. Safety alignment is when you basically punish the model for giving you the answer that you want, except the answer that you want is not the answer that you want the other people to have. as a big company. So, you know, you can't ask ChatGPT to give you the formula to make TNT, but you can find that out on Google, which is weird. So contexts look like this. What is a context? Context is just the words that come like as your prompt, or what comes the system prompt plus the prompt, whatever comes before the next tokens are predicted. So in an unaligned LLM, these are just like regular text. You know, this is an article about neural networks. What is a neural net is, and then it just goes up. You know, or you can simulate multiple conversations, like conversations with multiple people, not just dialogues, but like Alice, Bob, and Rupert having a conversation, and this could just go on within the context of the system. But when you instruct align them, you're gonna have this scheme. This scheme is basically written into almost every language model that you can get nowadays in use. So there's a system prompt that says what it is and what it's supposed to do. There's a user prompt, where that's where you fill it in, and then there's the GPT, and then GPT fills it in, or not just GPT, or like any sort of AI model, just fills in what it can, and then when it comes back to these three, it stops producing, and then you add this, and then you add your input, and then you keep on doing that. So it's kind of fake. Like that's the whole thing. Like the conversation is a lie. There's no conversation happening. It's just like the model is still predicting what's supposed to come next in the conversation. Yeah, basically. So then we have agents. When you build agents with LLMs, it's usually just different contexts, because in most cases, most papers, you have the same model. You just change the context. Oh, you are Agent Smith. Oh, you are Neo, or you are whatever. Make your character, and then have them play with each other. So you create two programs, or like contexts. Your chat agent generates the text responses, and your summary agent condensed text, and then you use this one to generate some response, and then you pass that response into this guy, and that's one way to do it. But you can also do like back and forth and simulate the conversation in the same way, except instead of it being user and GPT, you have the user being some other GPT. Super simple. So building agents. Oh yeah, there are two ways to do this. I'm going to show you some examples. I'm going to show you unaligned versus aligned. I'm going to show you some examples of how to build agents. So when you go on ChatGPT and you want to make an agent, it usually says, when it's prompting the system itself, it says, this is GPT, blah, blah, blah. But it turns out it's better practice to say you are GPT, because that's more like an actual conversation that you're having. You don't see, like, you go into a conversation, you're like, this is Bardia. I'm Bardia. You're GPT. Let's do the thing. It makes more sense within the context, basically. You have two types. You have the template type, which is where you give it like a structure that you want it to adhere to, or you can just give it a command, like, hey, do this, give me that, give me this response, give me that response. We're going to see more. And then you have long prompts versus short prompts. Short prompts are better. Long prompts take up a lot of context, and some stuff can get forgotten if it's too long. So let's look at some examples. So this, in OpenAI platform.openai.com, you have, over here you have complete, you have chat, and you have assistants. Chat and assistants are basically the same thing, where here you save your system prompts, here you don't. In complete, it's just autocomplete. So here is a list of 10 egg recipes, and then you do that one. And then basically writes that recipe. But here the way this worked was that the context is unaligned, so we have to create the expectation, and the way we do it is like we pretend it's a blog, and it's basically telling us what the recipes are supposed to be. On the other hand, chats, you've all used it, I'm sure. And if you want to build prompts, this is one way to do it. This is the command way, where you basically tell it what you want. It's like you give the user a score out of 5. This is creating GPT. You always do this, you do that. You describe what it's supposed to be, or you can give it commands. Here they pretty much mean the same thing. Or another way you can do this is giving it, let's say, let me see. Yeah. So here I've given it a schema. You can define a schema and be like, hey, I want you to answer with this template, with this structure. This will basically let you create structured text if that's what you wish to aim. That's what you aim for. That's what you wish to get. So I think that was sufficient. I'm not gonna go in detail right now. By the way, on Discord, that's where all this is gonna be like, if y'all have any questions, also during the presentation, please stop me. And on Discord is where we're gonna be, like, there's gonna be support. I'll be there to support each and every one of you over the next couple of weeks. Yeah?
Can you talk about function calls and assistance?
Function calls and assistance, it basically, okay, I can. You take that, what the way it works is that you take the output of the GPT, and as you're reading it, you give it a schema. Hey, like, if you open and you close a bracket, and then there's a function, call the function, put the output in there, and then continue. So basically, it's kind of like when you do printf in Python or something like that. You put the function within the text, and then you evaluate the function, and then after the function is evaluated, you generate the rest of it. Does that answer your question?
Could you give some examples with
No, because I wasn't planning for that, and I might if I finish this, I will show you if I do this. Anything else? Questions? Anyone? Anything? Anything at all? Okay. Has anything been unclear so far? Has everything been super clear so far? Yeah. Okay. Have you been underwhelmed? Have you been overwhelmed?
Yeah.
Okay, that's good. The slides are available, and if you're overwhelmed, you can always go back and get them. But if you're underwhelmed, I'm really sorry. Okay. LLM configurations. These things don't change no matter your model underneath, because they are basically transformer configurations. There is 3 things that are really important that you will see in every model. One is temperature. And temperature basically is a measure of how creative your model is, and how creative it is only means like how uniform the distribution of the probability of the next token is. What does that mean? That means if you have a 90% chance of we complete each other's 90% chance sentences, 5% chance words, 3% chance something else, what you do, and then 2% chance other. What you do is basically reduce that 90% and you increase the rest. That's what the temperature value really mathematically does. What it does functionally is that when it's lower, you lower the hallucinations. It's more accurate to your data set, and if it's higher, it's more creative. It comes out with like all sorts of random stuff. So if it's too high, it will just come up with like nonsense. But if it's like just enough, you might get some really interesting results. Context we talked about already, and context size is basically how many tokens a model can process at the time. And don't forget, tokens are basically the atoms of these language models. It's basically split up words, which is like and sentences. Like it's like E and space. That's the token. Also, Harry here sent me a link to Andrej Karpathy, the co-founder of OpenAI, has a full 2-hour tutorial on how to build your own tokenizer. I think it's a little bit long. My ADHD could never, but you might look at it if you're interested. So then let's talk about interfaces. This is where the cool stuff happens, where you do stuff. ChatGPT, obviously. The Claude, which is an Anthropic system. I don't use it much. Recently, we've had Grok with a Q. This is actually a 2016 company, whereas Grok with a K came out like 2023, I guess, Elon Musk's model. Grok is really interesting because they use this processing units called LPUs, which is just made for language model inference. So it's super fast. It is so fast, it will blow your mind. Let's see it. Yes. Who wants to give me a prompt?
This is the one on Twitter, right?
No, this is the one. This is a new one. This company was built in 2016. So the one on Twitter is Grok with a K, which came out like last year. This is an older company, but this inference system came out very recently, and it's super fast. Someone give me a prompt, please.
What's the difference between a GPU, LPU, and
Oh, what's the difference between GPU and TPU? You're asking me, or you want me to ask someone else? Okay, what's the difference TPU, like it is instant, and this is a mixture. So it's called a mixture of experts model. You see here it has 8 times 7b, so it's 8 7 billion parameter models, and that's one way to get accurate responses from your model. So you bunch together a bunch of smaller ones, and you get their answers. Yeah. So these are the proprietary ones. These are the stuff you need to pay for, right? If you don't want to pay for stuff, which is where all the good stuff actually is in the open source, or actually I should say open models. Kind of sounds weird, but so we have LM Studio. If you have a good GPU with like 8 gigabytes of RAM, you can use LM Studio, and you will let you like download models straight away from. It will allow you to download models straight from Hugging Face and then run them on your computer. It might also work with CPUs. I mean, it natively works with CPUs, but it's a little bit slow, and it goes on your RAM. So if you have a lot of RAM and a good CPU, you can also use it. Llama.cpp for an Apple or Linux user. This is great. I've heard great things. I've never used it myself. Hugging Face spaces. You'll see it here. I have an example lined up for you. Here. In Spaces, you have basically all sorts of models that are hosted on Hugging Face's own GPUs, and you can go in there and choose one and try it out. And it includes image models like SDXL. Differential diffusion is the first time I'm hearing about that. And then we have some API-based language model types, which are Hugging Face. Again, Hugging Face Transformers is a library that you can go on Google Colab, which is what I've also mentioned here. Google Colab is an interface where you can run code on a machine that is owned by Google, that has like powerful GPUs that you can use to train your models, and you can use to try out models, and that you can build complex systems with. And we're going to talk about some of them. Here, Grok also has an API if you want to programmatically generate responses. And then there's OpenAI Playground, which I just showed you. That's basically their API platform. It shows you what they can do, and then there's documentation. If you want to like make some code to do some specific thing, you can do that. So that's it for the transformer models, for the basics. You know, just a quick recap. This is what is really important. The configurations, very simple. Contexts and agents, and alignment, and basically how the transformer models work, which is by association of words. So diffusion models. This came out in 2021. It blew people's minds. Well, actually, it came out in 2020, but it found a resurgence in 2021. The way it works is that we have a network, an encoder-decoder network, in most cases a unit, excuse me. And what we do is we take, let's say, an image, and we progressively add noise to it. And every time we add noise, we train the model to remove that noise. So we give it the less noisy version as a Y, we give it the more noisy version as an X, and we're like, hey, find the difference, you know, is this a pigeon or not? And then like it iteratively learns to remove noise from some image. It all started with clip-guided diffusion in 2021. That's where the first text-to-image generators came from. What they did is that they took this clip, which is a vision transformer, which we talked about earlier. It has some, you know, it encodes some images and gives out a description. And we use that as a loss function instead of like MSC or something simple. We use this whole thing basically to tell us, is the image that's coming out the same thing as I put in text? And then we train the model. We're like, hey, is it not? And then move the parameters to make sure that it is. And then the generation becomes like this. You just give it a text, it gets encoded as a clip layer, and then you add that into the later latence layer. And yes? Okay. And I'm going to talk about latent. Basically, yeah, latent. Basically just means the output of the encoder. latent is not some. I mean, it is a hidden dimension, but it's not, probably not as mysterious. I mean, it is mysterious, but also not. I don't know how to explain it. It's very mathematical. It's very simple, but it has crazy properties. That's the best way I can say it. And then you add this to the latent layer, what your text is versus what the diffusion model is doing. So depending on how much you want that to influence, you have a parameter for that. We'll talk about that later. Yes?
Yes, on the next slide, we're talking about, yeah, so usually for the loss function, what we're trying to do is say, like, minimize error.
Yeah.
So, like, intuitively, how are we doing that?
The error is basically, so we're not getting a description. First of all, that's a lie. We're not getting a description. We're getting a latent vector out of the clip, and then we try to match the latent vector to the encoder. Encoder is latent there. So we basically get these two to become the same, so that the next time when we give it a text, it matches. It basically learns the same distribution as that latent. So when we add it, we're like, hey, modify the latent image in that direction that I wanted, given that text. So yeah, this is an actual output of a clip-guided diffusion. 2021 hasn't been that long. It has not been 3 years. I'll tell you that. Then we had stable latent diffusion. There's a bunch of models that came in between. I'm going to showcase them, but this was the one that became stable diffusion. Same training process, except now instead of training just the diffusion model, you have a VAE. A VAE is, again, very similar. It has an encoder and decoder, compresses data into a lower dimension, and then expands it into higher dimensions to give you the results. Except here we're training both of these models. We train the VAE based on the clip text encoder, and then we train the units encoder dependent on clip. So what it does is that it has a singular representation for images, and it turns out it increases the quality by a lot. And basically the units here would be denoising, not the image, but the representation of the image in the latent space of the VAE. So there's that. Don't think of it too deeply. It's just to say that we wrapped it in a bigger model, and it's doing better. And and here's a scheme for an image to image. So we can do image to image, right? We can do 50% denoising that image, and if you give it a noisy image, we will do so there's these samplers, and what they do is they figure out how much they have to remove noise per iteration, and you do 30 iteration on a base stable diffusion, but now there are models that do 1 iteration, and that's it. This is an interface called Comfy UI, which you can use locally. I think also remotely, and I put a link there, but I haven't tried it myself. I hope it works. And it basically gives out the whole entire high-level structure that you need to know. So basically, you load a checkpoint, which is you load a model. The model has a clip encoder. It has a VAE, which is the other auxiliary model, which encodes the image, and then you have the model itself. So you take some text and you add it as conditioning. You have a positive prompt and a negative prompt. And then you have this empty latent, which is just noise that then we run through this and then becomes latent. And then we do the denoising, and then we decode that and we get that. Very simple, very straightforward. Questions? Questions? Answers? No? Okay. Yeah.
Are you gonna show us some stuff that we can actually do?
Yes. Yeah, coming up, right up almost. Image synthesis. So we already went through this. I'm not gonna go over it again. Here are the main parameters or stuff, adjustable stuff that you will be playing with, including the image that you probably feed it. But on almost all the systems, even Sora, it's the same thing. Because Sora is a diffusion model. Everything that's coming out now they have these properties. So the first one is the model or checkpoints, and there's like literally thousands of them that you can choose from. Hugging Face or Civet.ai. Civet.ai is like a place where people put their own like fine-tuned models. Then you have VAEs. VAEs, they don't change much. Some people train their own, but most of the time they're the same. If different models have different VAEs. You have positive and negative prompts. Basically, the text that gets encoded. Positive prompts are what you want in your image. Negative prompts are what you don't want in your image. I think it's self-explanatory. And then there's a CFG. CFG, it means clip. It's kind of like clip guidance scale. Think of it like that. Basically, it tells you how much you want the text to affect the image. I can't remember what the abbreviation stands for right now. Basically, yeah, it tells you how much should the image prompt. Clearly, I didn't finish this. Latents. That's your noise or your image. So you encode the image or the noise, and that's your latent. Sampler is the method that you use to remove and inject noise. And usually there's a default. In most cases, you'll see it. It's called Euler. Use that one. It's great. Then there's denoise strength. One is complete noise. You're denoising complete noise. Zero just gives your own image back, so there's like no changes. And then seed is for reproducibility. So if you use the same seed, you get the same results. You should anyways. You can use these models to do text to image, image to image, text to video, image to video, and video to video. And there's like, you can also do text to voice, text to sound, because you can represent voice and sound as a two-dimensional spectrograph. So image synthesis started with GANs in 2014. I'm not going to go over this. I'm just going to show you the results. Okay, so we had Deep Dream in 2015. This kind of broke some new grounds, and people, I remember reading articles about it. It was on TV and stuff. And then we had style GANs, which was like, a GAN is a generative adversarial network. They train two networks to, one kind of becomes the loss function for the other. One's a discriminator, one's a generator. And this guy's saying how wrong you are. This guy is trying to fool this guy. And they play with each other, and they get better and better at what they do. This is called a style GAN. This was DALL-E, OpenAI 2021. This is not a diffusion model. This is a transformer model, except it's like vision in reverse. They trained it in the sense that you give it some text, and now you expect some tokens to represent an image. And it turns out that it did pretty well, but it's very expensive to run. And you also can't exactly predict how many tokens are going to come out of the model. How many? Like you can't ensure that you're going to get an image out of it if something goes wrong. And then we had VQ-GAN clips. That was 2021. It looks really bad, but it was super easy to run, and there were like a whole bunch of collab notebooks that people used. And this is the same, almost the same stuff, except now that it's been used over videos and has been turned into animations, and each of them works in a slightly different way. So here is like we're doing every frame, and I think it's like following, bringing some stuff from the previous frame to the next frame. This is style GAN. You're just moving across the latent dimensions. You're like changing parameters inside the model, and as you're like moving those numbers up and down, you're gonna see like different topologies and different kinds of images come back. And this is lucid sonic dreams, and all of this here, by the way, very important. This, for example, links to a Google. This links to a GitHub or a Google Colab, which is basically you will just click on these and you should be able to use them, or brings you to a place where you can use these models for your own, if you want. This is a VQ-GAN clip. This was one of the first models I used. It was mind-blowing, really cool at the time. And then we said bye to VQ-GANs in 2021. We got to diffusions. And it started with disco diffusion to 2022. It was great, and a couple of people here that I know already used it. Those were the times, man. Like that's when it was like really ramping up, and it was getting like really exciting. Oh shit, we can make whatever we want in a computer now. That's like whack. Then we got latent diffusions, which I talked about. Disco diffusion is, I think, the same thing as clip-guided diffusion, except it uses, it does clip-guided diffusion, but the way it does it is that it does it on patches of the image. And this sort of sort of patching algorithm was written by this lady called Catherine Crossan, who has done a lot for this community, and her name is really not known. Then we had centipede diffusion. Centipede diffusions would take output from a latent and then do disco diffusion on it. And then we had stable diffusion 1.5, which came out in 2021. The same people who invented latent diffusion, Robin Rombach. This guy called Emad Mostak was this British venture capitalist guy, gave this guy gave Robin Rombach and his team like $500,000, and then they trained stable diffusion for like a week on a data set that was by Lyon. And Lyon was a Discord community, it still is a Discord community, of random people, probably in their basement, some researchers, some not, who just gathered around the data set. And so these guys just made the model based on that. And the results were, well, really good compared to all the other models we checked. And then that started a whole, Cambrian explosion. Then we had DALL-E 2, also diffusion, DALL-E 3, diffusion as well, Midjourney, also diffusion. They say they have their own model, I don't believe them. SDXL is a newer diffusion model. I think the dates here are not right. I think for SDXL it's 2020. Anyways, it just started a whole bunch of stuff. Then some people like me who were just like fascinated by moving images were like, we can apply these things to to frames, or we can make frames after frames, generate stuff. So here's like an example of this. On the left is disco diffusion, and this is PYTTI. And the way it works is not diffusion based at all, but it has a clip part to it. The way it does it is basically turns the whole image into something a GPU can process, and then the loss is basically what clip expects, and then you change the singular pixel color values. This is the forum. And the forum, the way it works is you kind of like you generate a frame, you zoom in, and then you denoise like 50%. You add 50% noise, and then you do another denoising, and then you go in a little bit, zoom in a little bit, like make it bigger, and then just do the same thing over and over again. Stable warp takes stable diffusion, and then it blends frames together, as well as an intermediary flame using the optical flow of the images, which is just the difference of where did each pixel move between frames. So all these links, you can go and you can use these things. And I will go over them if you have time, basically over how they look like and how you're supposed to use them. This is by Midjourney Man, great guy. This is the same thing as before, it's PYTTI, but we add stable warp on it. So we blend the frames with each other, and we do like stable diffusion denoising. And this is animate diff, and I'm going to talk more about this in the next workshop, not today. And there's some new models: stable cascade, stable diffusion 3, which looks really good and can generate text as well, and stable video diffusion, which is like a video model. And I put like a simple cheat sheet and resources, but I'm going to be putting a lot more on Discord. So Discord is where you're all going to be doing the work. Like and this is to just guide you to like, here are the resources, here's what you can do, here's what these models are. And then on Discord, I'm going to answer all your questions. Here's some artists you can check out. I'm not going to go over them on Instagram. And the interfaces for stable diffusion and those kinds of models. I've listed them here. So number one is Comfy UI, but this is mostly local. Like I said, there's a remote version that I've linked somewhere in this slide. I'll show you. If you ask me, I'll send it on Discord as well. And it's great because you can see exactly what's going on. You have a lot of room for improvisation and like adding stuff and trying out new stuff. Then there's Automatic 1111. I'm going to go over these again at the end if there's time. Dream Studio by Stability.ai, which is an online thing. It's super cheap to use. Again, like this is paid. These two are not. And you can also do most of these things for free on Google Colab. Then there's Runway ML and Pika Labs, which is text to video and image to video. You can take an image, let's say from Midjourney, or I forgot to put Midjourney. There's also Midjourney. I'm sure like a lot of you have heard of it. Midjourney, you can, same principle. It's a Discord bot that takes your prompt, feeds it to a diffusion model, and gives you back the output. And there's a whole bunch of models like we just saw on Hugging Face Spaces. Over here, just go to huggingface.co, and then you see the spaces, and you're gonna see that there is that. All right. So yeah, they even have like a little bit of a animate this situation. So it takes stable video diffusion, and then I guess passes through that. Kind of feels like, let's say, stable cascade. They usually have examples, some preloaded example on them. So let's see. Yeah, astronaut riding a green horse. That's a stable cascade output. It's free. You can go on Hugging Face Space. It just takes a while to generate. That's it, and then it gives you that. Okay. Before I move on to post-processing, questions? I'm taking. Now's a good time. Yeah.
So the encoder, decoder, those are the neural networks.
Encoder, decoder, it's one neural network, but it's two parts. One part is we reduce the dimensions of your input. So we basically multiply them by numbers, and we make smaller and smaller lists that are supposed to represent what came before.
In the dimensions, they're like a little circle. In the drawing.
I'll show you what the dimensions. Yeah, the dimensions, yes, they are the little circles. Yes. So I'll show you. Let's go back to the beginning and go over this, because this is important. Understanding this, well, it's fundamental. Okay. So this, by very definition, this is an encoder here. So you see that there's like 8 dimensions here, which means we had 8 variables, and then we did that multiplication, and then we had 7. Yeah, and then the multiplication, basically, I'm going to do a little simple example of one way I like to visualize matrix multiplication is if you have, let's say in a 2 example, let's say x0, x1, and then I have like, w0, w1, w2, w3. I like to write them like this, and you will know that the stuff, like this is going to be the dimension, which is going to be 1, 2, like 1 row and 2 columns, right? And you're going to have y0 and y1 here. And this will basically tell you how big this is. So if you want to make, if you want to increase the dimensions, what you can do is you can take this x0, x1, and then you can multiply it by a list that's slightly longer. So like w8, or like let's say 0, I'm sorry, bad handwriting. But the thing is, this list now becomes longer. It becomes 8 values instead of 2. So you can kind of expand, or you can reduce the dimensions of what you want. And here, I'll have another example here if you want to see like the big view. This is just a massive matrix multiplication. I did not write this by hand. I asked ChatGPT to do it. But basically, yeah, you take this column, you collapse it onto this row, and then the thing that comes here, the next number, like y0 becomes the multiplication of like w00, and x0, x1, w10, and then so on. And then you sum. Exactly, you multiply and then you sum it all up.
And then you add text and it like
expands.
these represent.
Could represent text. It could in large language models, yes. Yeah. Yeah, that's the idea. You're shrinking the value. So first, like let's say you have an image has like let's say we have an image that has this like 10 pixels by 10 pixels. You have 100 pixels representing that image. We can make it like go from left to right and up top to bottom and write it as one long list. And then we can do this matrix multiplication, and then we can just reduce that list to like 50, and then to 40. And then to basically the goal is to reach a point where you have the maximum number of Like you have the minimum number of dimensions that represent what you had before. And then you can train the other part of the network, basically learns to regenerate the same thing. Clear? Any other questions?
Yeah, and then when you want to generate different things,
Mhm.
then you add more stuff to it.
Yeah,
To generate
you expand it. That's right. You expand it by changing the width and the height of this matrix multiplication. Question? Anybody? Nobody? Have I been clear? Have I been unclear? Okay. Have I been so clear that you have no questions at all?
Yeah, it's just about
Okay. I know. But I'll give you the content and then you, yes.
For why you need the description of the movement of the
The description. Are you talking about the transformer model? Okay. Hold on. I'll explain. So here, I guess in this case, which is the description, what is happening here? Like these two are only during training. During inference or generation, you don't give this description. So this is just basically to say that if you want to correlate these two things, you give it the image and you give it the description, and then it will learn to generate that. But when you want to use it, no description at all. So and then this part of the network, this beginning part, is not run, except you're gonna have your image go in through here, and then you're gonna go take it through there, and it will go and it will generate the description for you. Except there are cases where you do give out some part of the output first, which then gets processed into the decoder before giving out the description. I feel like I haven't been fully clear. Yeah? Okay. Anything else? Yeah?
Yeah, how does the GAN and this diffusion model compare?
GAN and diffusion model. Basically, the way they're trained. So a diffusion model only knows how to remove noise from a noisy image. That's all the diffusion model knows. A GAN, on the other hand, has two parts. It has a generator and a discriminator. And then the generator, you give it basically a latent, and then it will just transform that into the image. There's no, like, it doesn't find a way to denoise it or anything like that. It just gives you the whole output. But the problem with a GAN is that it doesn't generalize that well. It doesn't allow you to come up with high quality images. So that it kind of fails there. It's more direct in terms of how it works. It has discriminator, generator, and then you just use the generator to be like, hey, here are some input layers that I want to tune these parameters. Okay, like put the X1 here, that, put the W1 here, that. There's also a website there, I think. GanBreeder, Artbreeder. There you go. This will give you a really good one. I don't want to check that. So these, as far as I know, are supposed to be mostly GANs, unless they changed it. I think they did. And basically, they had these parameters that you could play with, increase and decrease, and basically, the weights inside directly translate to stuff you see in the image. So there's like a neuron for dog or cat, and then you can just like move that to 0 or 1, and you'll see like there's a difference. Sorry, I can't find that right now. I don't want to spend too much time on that. But is that clear? Like the parameters in a GAN are directly linked to the image, and the input is just like a latent, and then it gets decoded into an image. Whereas For diffusion model, those parameters don't mean anything because all they do is like they guide the model to denoise the image a little bit.
So basically, the GAN model is like the parameters are important.
Yeah, in a GAN model, the parameters mean something. The parameters you can change some parameters somewhere, and it will mean something in the image. Like remove a mountain, or it will like add a mountain. Like there will be a parameter for mountains. There will be a parameter for seas. There will be a parameter for woman. There will be a parameter for man. Very much like the human brain, I guess, in that sense.
When you talk about parameters, does that mean like learning rates or?
No, parameters are the weights, the W's.
The kernels?
Yeah, the W's, like the thing that gets multiplied, that multiplies two nodes, two values. Those are the parameters. The learning rate is basically what you use in the optimizer to minimize the difference between what you have and what you want. Anything else? Nope. Okay, post-processing, really briefly. Usually when you generate these images, these models are expensive and you don't want to, spend like, I don't know, a week generating a full HD video. So what you do is that you generate them, first of all, a little bit more choppier over time if you're doing animation. And if you're doing just images or also animation, you do it at a lower resolution, like let's say 512 by 512. And then you upscale it. First I want to talk about upscaling. Upscaling is when you take a low resolution image and you increase the resolution. And there are tools for that. There is Topaz Gigapixel for just individual images. There's Topaz Video AI, which does both interpolation, and I'll tell you what interpolation is in a minute, and upscaling. And there's Magnified AI, which is cool, but it's basically this other thing, Ultimate SD Upscaler, which you can find it as a Comfy UI custom node, which you basically, it's like a mod. You copy and paste some files in there and it works. And then you have all these models that people have trained. Some of them are really good. Like these last three, some people swear by it. These two are a little bit older, the ESR GAN and the DSR. And this Ultimate SD Upscaler basically uses Stable Diffusion itself and like does patches of the image, adds noise and then denoises it on a bigger scale. So you increase the scale of a part of the image, and you just do bilinear interpolation, which just means it's going to look a little bit jaggedy. It's not going to look good when you upscale it. And then you add noise, and then you denoise. And that would be your ultimate SD upscaler. That's upscaling for images and for videos. And interpolation is basically the act of finding the frames that are in between. So if you have a low frame rate per second, low FPS video, and you want to increase the frame rates, you do frame interpolation. So a lot of these videos that I showed you guys here, like this, has plenty of interpolation in it. So does this. You kind of see the artifacts in disco diffusion and stable diffusion better. If you use them, it becomes like super obvious. So basically, there's like patches of the image that kind of get warped from frame to frame. And also these ones I think have interpolation. This one for sure it does because animators usually does like, you can't do that many frames with it, and you get like 10 frames per second, but then you interpolate it and then you upscale it, same thing here. So it's an important part of the process if you want to make something that looks nice. And so time for some AI ethics. AI is cool, AI is awesome, but it could also have a lot of problems, both societal, cultural, and for yourself, for the sake of your own sake and for intellectual property. Very briefly, I'll mention what they are. So first, we're going to go through the 5 principles for AI, which was suggested by Encode Justice, which is, number 1 is you must do good. Number 2 is, like Google, don't be evil. 3 is autonomy. You should be able to make decisions without the AI. That's right. You are not the AI's tool. The AI is your tool. Justice, your project should try to fix something. So, or like fix a nice, fix my boredom with a nice image. I don't know. You can think of it that way if you want to, just for creative purposes. And then you should understand how it works, which is kind of the point of half of what I talked about today. So the first problem that comes about is representation. This is actually a very, very important issue. So you have a true data distribution. For example, in the first case, you have the guy on the left represents all the white male CEOs. You might have like 90% of the CEOs in the world being white males. It's unfair. It sucks. It's unfair. It's not right, but it's true. It's a fact that you can't deny. But the problem is that when you train a model on it and you ask for the image of a CEO, the model is going to give you probably white males. The second case, the augmented data set, this is a recent case, something you can do now, you can do before. Because of generative AI, you can create new data and inject it to your data set. And also use alignment. So basically, you punish and reward the model based on what it gave you. But the worst kind is pruned or misaligned data set. I personally am so against this because first of all, it lowers the amount of data you have in your model, so it ruins the way it works. Second of all, you're being unfair to the people who did already have representation. So instead of empowering others, you brought others down in some sense, in terms of data, but like in terms of representation within the data set. So we have underrepresentation. For example, Midjourney before you ask for a beautiful woman, all the women are Caucasian. There's nothing wrong with that, but there is something wrong with the fact that the model does not realize that, hey, beautiful women can be women of color too. But then we also have misrepresentation. This is real. This is real. This is not a meme. This actually happened last week, and Google Gemini shut down its people, like its services to generate people, because apparently it was so biased against white people. So I guess it can go both ways, So it's important to always keep a balanced view and try to be fair to everyone. Another thing is intellectual property. So if you want to train a model, so in case of like Stable Diffusion versus OpenAI has a lot of money. It's so easy for them to get like a lot of data, which they can train their models with. Whereas Stable Diffusion, they didn't. So it was just a bunch of people like banding together and finding some info and creating, this model. However, there's IP issues for that. People are like, oh, that's my art in your data set. It's not supposed to be there. What are you doing? To some extent, they're right. Maybe they don't want it there. They have to have like an option to opt out. But this is basically a Virgin's view. Whereas we have the Chad view. The Chad view says you can use synthetic data and alignment and make your model better without actually stealing other people's data. So if you already have a base model, which you already do, we can just use alignment and we can just use the synthetic data that we get from it in order to make it better. Amon Mostab, the same guy who is like now the CEO of Stability.ai, who created Stable Diffusion, paid the money for it. He's now doing, he wants to do a Sora competitor, and he's asking people on Twitter to go and upvote the videos they like and downvote the videos they don't like so that they can align their models and do better. And when it comes to generation, and you want to generate an image or or make a video or something like that, always think of this quote by Picasso, which is good artists copy, great artists steal. So if you're taking one person's intellectual property, if you're taking a model that's based on one person's work, or you're taking a text prompt that specifically targets an artist and kind of like makes everything in their style and their style only, and you're passing it off as your own, obviously it's not the right thing to do. I mean, I think it's kind of obvious. Like, you wouldn't want to have someone doing that to you. So you definitely don't want to do that to someone else. But I think it's okay to like, mix and match, because that's not something that the artists themselves can do. That's something you can do as someone who's doing image synthesis, which is great. And your safety, yes, this is also very important. If you're downloading models, dot checkpoint and dot pickle models, if you're doing it locally or remotely, doesn't matter. But if you have like a decent GPU with 8 gigabytes of RAM, preferably NVIDIA, you might be downloading your own models. And when you do on your own computer, try not to download checkpoints and pickle files, because these, basically when you open them, they are Python programs and they can run on your system, and someone can put Bitcoin miner. Someone can put something to like a Trojans or some sort of code you don't want, and it will run. Safe tensors is just a list. It's just a list of numbers. So they're safe. You can download them and use them as models, and most platforms and local stuff have support for that sort of thing. And here's a glossary. So I'm just going to go over this very quick. So Doge style token, smallest piece, word or part, very basic, much start. Embeddings, info to vectors, many dimensions. For comparing, dot product can use, but we're not even going to talk about that. Such similarities. So it finds the similarities between things using dot products, but that doesn't matter. Positional encoding, we didn't talk about that, doesn't matter. Encoder takes inputs, embeddings, makes sense into condensed form. Very understanding. Decoder takes the condensed form, makes output, very creation, much expressive. Latent space, hidden space, very mysterious. Encoder's output, decoder's input. Basically, it's the weights in between. Much potential. Self-attention, looks at self, understands context. Very aware, so relation. Sequence model, like transformer, uses order, tells story, much flow through narrative. Transformers uses embedding, self-attention, encoder, decoder, very powerful, much transform. VAE, encode to latent, then decode, very generative, very probabilistic. These are probabilistic models, by the way, but it doesn't matter. You don't have to care about that. Loss functions measures error. Such goal, you will have the goal, you have what you want, you have what you got, you minimize. Tells how bad, very important. And then gradient descent follows loss downhill in that big space. Adjust parameters, much optimized, so smart. Diffusion, start noisy, denoise step by step. Very gradual, much refined. Latent diffusion, encode with VAE, then denoise, then decode. One very creative, much generative. Such learning, very AI. Wow. Thank you. That was it for now. We have 10 minutes for questions. Okay. Oh yeah, one more thing before we even begin that. For the next workshop, which is on Wednesday, I would like everyone here on Discord to share some piece of generative media they made. Doesn't matter. It could be you could have made a GPT. You could have made a image with Midjourney. You could have made an image with Comfy UI or whatever. And all the resources are in here. So I was just giving you the basics. The resources are mostly going to be in here. I'm going to add more resources on Discord. And the only way to learn this stuff is to use FAFO. Does anyone know what that means? Goddamn right. That's what you fuck around, you find out. That's how you learn. There's no other way. Okay. This is just to give you the field, and there it is. So for Wednesday, please come up with something very simple and a little sentence saying what process you used to get there. That's it.
Sorry, before you leave, everyone. Also, we can reserve 10 minutes. So if you want to ask questions, maybe even try anything that we've shown today, ask Bardia. I think no one is after us in this room, so obviously you're welcome to hang out. But just before you leave, 2 things. Be sure to fill out the form, the pre-survey thing. Please do it. And also come see me or anyone in this room to sign in if you haven't. And also,
okay. Hi everyone, I'm Cleo. I'm co-director of Encode Justice Canada, so we got some AI ethics content today. But I'm also here to talk about teams formation. So you might have seen in the advertising that we're kind of doing some sort of project in between the second and third workshops and teams. So if you're part of the Discord, you'll have seen the teams channels are public.
No,
right?
I don't think so.
So we'll make teams channels public. We're going to send information after this. Please make sure you're in the Discord. But the goal is, this is kind of a mini assignment between the first 2 workshops, is to just kind of
individual.
Right now, individual mini assignment just to kind of play around with the technology. But in between the second and third workshop, we're going to have you working either in teams if you want, or just individually. We'll have another channel for all the individual people to kind of work on something. a little bit bigger with the tools that Bardia will give you. So this is a good overview. You'll get more information on Wednesday, but please make sure you're in the Discord so that you can get all of those resources. Yeah, and as Bardia said, this is now time for questions, but thank you so much, Bardia, for the lecture.
Hopefully I'll find it even slightly useful. I think. Okay. Any questions? Now's the time. Oh, yeah. Yep.
Can you show us an example like how to use this?
Yeah. What do you want to know how to use?
Like just an example.
Okay.
An example what we can do for Wednesday, for example.
Okay. Sure. Sure. Why not? Let me give you an example with Midjourney. It's very simple, very easy, and not just Midjourney. We're gonna come here, and Midjourney is a Discord bot, as they said. I already have this, so why not take this and turn it into a video and see how it does? So okay, no, okay, I'll start from the beginning. So Midjourney bot, it's a bot. It's like you have some trial amounts of generations if you want, and then there's like different paid tiers that if you want to use. The quality of the images are usually really good, which is why I use it. So we say imagine/imagine, and then you give it your prompt. Your prompt would be, so here's the thing, you don't have like a lot of these proprietary types, they don't have CFGs, which is the parameter I said. They already have it like encoded in it, it's hidden from it. So we're just gonna give it a prompt, and the prompt is gonna be, give me a prompt. No, this is an image generator. Okay, so we don't say generate a software player. Okay, so here's one thing. These models were trained on image captions and images. So you have to kind of like think about, this has changed a little bit, but overall, you have to think very descriptively. So you don't give it a command. You describe what you want to see. So you say soccer player. Don't say generate a soccer player. You say soccer player. Do you want anything specific about the soccer player? Man. Huh?
Scoring soccer player while scoring a goal.
Okay, scoring a goal. On the moon? Yeah. On the moon. Anything else? All right. Suspense.
Do you know that you are still used to training Midjourney?
Right now, it's just alignment. So I think so, because they have their own data sets, right? And they even went through a period where they had people, thumbs up with thumbs down their images. So they basically did reinforcement learning on that. Exactly.
How did you get the bot?
How did I get? Oh, midjourney.com. I think it's linked on the slides. So I'm pretty sure it is. If it's not, hit me up. I'll put it on Discord. I'll make sure. But you just Google Midjourney. That's it.
You want something to
So for Wednesday, we're gonna talk a bit about fine-tuning models. It's coming. We're gonna talk about fine-tuning models. We're gonna talk about LoRa's, basically how you can change the output of your model using low-rank adaptations. Is what they call it, and parameter-efficient fine-tuning. Basically, how to fine-tune a small number of parameters. Okay, here it is. Here's a man on the moon scoring it. Oh, he's as if he's scoring the moon itself. Which one do you like? Let's give you a better view. I like that one too. Yeah. Okay, let's do that. So I'm just gonna take this, and then I'm gonna come over here, and then I have Pecan, I have Runway. These are two image to video and text to video generators. I'll just take this, and I'll feed it here, and I'll be like soccer player scoring a goal on the moon. And here are the parameters. See the consistency with text? That's the same thing as the CFG parameter that I mentioned in the slides. So basically adherence to the text. The thing is, because we already have an image, I mean, if we want our image, if we want our video to be a little bit smoother, lower this thing. That's how I like it. You don't have to. And then you have the strength of motion, we're going to leave it at 1. The way these work is basically LoRa's. I'm going to talk about that. Yeah.
Are you using the default settings, or you have like your own settings?
No, here the default settings aren't that many, so I just changed it. So I was like, strength of motion is like 1 is good. I don't want too much motion in it. The consistency with text, you know, I just lowered it. I didn't use a seed because I'm not trying to get the same thing again, and I didn't use a negative prompt because I don't know. I don't know. I don't always do it. Some people do it all the time. That's up to you. So while this is generating, okay, I was talking about what I'm going to talk about. LoRa's animative. I'm going to talk about how animative works. Control nets. You're going to have this thing called control nets on most of these interfaces, especially if you're using it locally or if you're using something that's, you know, on a remote server that you have access to. You've set up that you're using, not some proprietary software like this. You're going to have the ability to condition your model, your images and your videos, not just on text, but on properties that you extract, features that you extract from the image. Let's say if there's a person standing, you can do a body pose. So you have another algorithm, simple algorithm that finds a pose of the person that's in the image, and then you keep the pose, and then you can like do denoising, and then we'll keep the pose of the person there, but it will change the content completely. Anyways, here it is. I think the motion is a little bit low. Sora. Oh yeah, and Sora. I'm going to talk about how it works next workshop. It's actually super simple. It's nothing you haven't seen already. Sora, we don't have access to it. I can't do it. Oh yeah, there is a video. I'll show you that for sure. I'll just go on that website. I don't want to go through Sam Altman's Twitter page. He does a lot of shit posting. So yeah, this is the feature. The only thing that makes a model like this, well, it's not. What am I hyping up? It's not even coming. Come on. Come on, bro. Okay, here. We're just gonna use the background for a second, so everything is loaded. This is all AI generated, right? Entirely. These flying paper plane birds. The only thing that makes Sora special is the simple fact that OpenAI has a lot of money and that they can spend it on compute and data. That's literally it. They probably paid a ton to Shutterstock for the videos, and they use GPT-4 to find the captions of what the image is saying, so that when you're using GPT-4, you can use like natural language in order to prompt the thing. But yeah, that's basically it. There it is. There's Sora. Sora's great. Looks great. There it is. Yeah. This is AI. This came out like last week. Yeah, we're getting there really fast, guys. It's crazy. Yeah. Most likely within the next couple of months, Stability AI is going to release a model that is going to be maybe not exactly this good, but very good, like on par, like competitor in a sense. And you're going to want to use that model locally. So the sooner you learn to do that, the more you can do this stuff without paying OpenAI, which is great. I love OpenAI, don't get me wrong. That's one prompt. Yeah. It's just it's continuous generation based on one prompt. Yeah, here's another one. Feeding the two. Buffy demon. Yeah.
So let's say you do another prompt to upload this video, or
Yeah. Check this out. Yeah. So they already figured this out. So the way it works is also like, it's also available in stable diffusion. So the guy who made Sora, Tim Brooks, he also first came up with something called instruct pix to pix, which is basically give an instruction and you're like, hey, make this thing red or make this look like that. And then stable diffusion takes that and does a little fancy schmancy math magic to it, and then you get out exactly what you asked for. But here is, is this an example? Yeah, it's the one with the car driving. That's what I'm thinking. Hold up. It should be there. Let me know if you find it, Harry. Let me know if it's on this page.
It's that one. You tested. Where they take another video and they just made it, go into like.
This?
Yeah, that one.
I don't think so.
Yeah, this is the model that they use, and then in the back, they add like the winter village from another video.
Yeah, yes. No, it's not. It's not on this page. Let's look at the technical report. I think that would be the one about world simulators. Yeah, this might have it. So yeah, Sora is also a world simulator. This is the state of the art right now. It's a world simulator, meaning that you can basically generate Minecraft and then write down what exactly you want your character to do in Minecraft. So it like builds the world and encodes the motion of the character. Content with images and videos should be here. Extending generated videos, video to video editing. Yes, there. So yeah. So we had. Let's see. Oh yeah, here's a really good one. So we have this image. All of this is AI generated. This is, I think, AI generated. That on the right is AI generated, and the one in the center is like the mix of both. So you can like mix videos, or you can put a video and be like, hey, turn this like that, and then we'll do it. Oh, there it is. That's what you were talking about. Yeah. So yeah, they basically took this video and they like prompted. It was like, add a Christmas village at the end. That's what it did. There we go. Or yeah, they had this drone thing, and then they had the butterfly thing, and then they made the drone butterfly thing. Drone goes in. It's cool stuff. So Google did it first, by the way. Google has had something similar to this before, but they never released it because Google is really good at making cool stuff, but then not releasing it. Huh? I don't know. No, that was some proprietary thing they didn't tell us about. Like I had to learn it from some other person. Anyways, anything else? Yeah? No? All right. Thank you. Thanks.